In this video, we're talking about resistive inductive series circuits. And to start, we're going to look at a purely resistive circuit. I have a crude one drawn here. We have 120 volts AC power supply, and that's wired in series with a 120 ohm resistor. This is a purely resistive circuit. When current flows through the circuit, that current is in phase with the voltage. And we're going to calculate these values over here. The resistance of the resistor, we're given that's 120 ohms. The voltage E sub R, it's 120 volts. We only have one load in this circuit. Now the current flowing through the resistor, that's this current here, I sub R. We use Ohm's law to calculate that. And Ohm's law is voltage divided by resistance equals 120 volts divided by 120 ohms, and that gives us 1 amp of current. For power, the formula is the voltage across the resistor times the current through the resistor equals 120 volts times 1 amp equals 120 watts. Now we're going to look at a purely inductive circuit. We have a 120 volt AC power supply at 60 Hertz, wired in series with a 1.2 Henry inductor. The inductance of the inductor is given, 1.2 Henries. And then I'm going to jump down to the voltage across the inductor, E sub L. There's only one load in this series circuit, so the voltage across the inductor is 120 volts. Now I'm going to jump back up to the inductive reactance. That's the current limiting thing in an inductive circuit. And we know that formula equals 2 pi FL equals 2 times pi times 60 times 1.2 equals 452.4 ohms. Now that we have the voltage across the inductor and the inductive reactance of the inductor, we can use Ohm's law to calculate the current through the inductor. And we do that by, again, using Ohm's law. That's the voltage across the inductor divided by X sub L. In Ohm's law, I'm substituting X sub L for R. So that equals 120 volts divided by 452 452.4 ohms, and that equals 265.3 milliamps. And now that we know the voltage across the inductor and the current through the inductor, we can calculate the reactive power at the inductor, and that's E sub L times I sub L equals 120 volts times 0.265.3 amps equals 31.8 bars, volt amps reactive. And that brings us to this resistive inductive series circuit. We can tell that this is a resistive inductive circuit because it has a resistive element and an inductive element. We have lots of different values that we need to calculate. We are given the resistance, the inductance, and the total applied voltage. We're also given that the applied voltage is at 60 Hertz. Because this is a series circuit, it's best for us to figure out what the current is. The current flowing through a series circuit is the same throughout the circuit. The same current that is flowing through this wire is flowing through this resistor, is flowing through this inductor, is flowing through this wire, and is also flowing through the power supply. So whenever we have a series circuit, try to focus on getting the total current of the circuit first. Now, to do that, in this case, we need this impedance, Z, total impedance. To do that, there's a formula. If you look at Appendix B in the back of the textbook, you'll have this formula. It's also in the chapter. And that is the square root of R squared plus X sub L squared. Okay, we have R, but we don't yet have X sub L. So I'm going to jump to X sub L. This we can calculate with the formula that we know quite well. We've seen this formula a lot. Two pi times 60 times our 1.2 henries, and that gives us 452.4 ohms. So now we can come back down here and we can finish this calculation. For 52.4 squared, and this gives us 468 ohms. 60 ohms. I'm going to write that again, hopefully clearer this time. So now we have the total impedance of the circuit, and that allows us to calculate the total current flowing through the circuit, and that's Ohm's law. Where we're substituting impedance for resistance in Ohm's law. So that equals 120 volts divided by 468 ohms equals 256.4 milliamps. Because this is a series circuit, we know that the current flowing through the circuit is the same for every element. So now we know the current flowing through the resistor is the same as the total current, and that's 256.4 milliamps. It's also the same current that's flowing through the inductor, 256.4 milliamps. So now we have a lot more information, and we can calculate the rest of the elements. I'm going to focus on the resistor. We have two more values to calculate. For the voltage across the resistor, we're using Ohm's law, and that's I sub R, the current flowing through the resistor, times the resistance, equals 0.2564 amps times 120 ohms equals 30.8 volts. Now that we know the voltage and the current through the resistor, we can calculate the power dissipated at the resistor. That's the power formula. That's the voltage across the resistor times the current through the resistor, 30.8 volts times 256.4 milliamps, or 0.2564 amps, and that equals 7.9 watts. We can use the same concept to calculate the voltage across the inductor, again using Ohm's law. That's the current through the inductor times the inductive reactance, equals 0.2564 amps times the inductive reactance, which is 452.4 ohms, and that gives us 116 volts. Next, we can calculate the reactive power. This formula is also shown in the chapter and shown in Appendix B. That's the current flowing through the inductor squared times the inductive reactance. Times the inductive reactance. And that gives us 29.7 bars. And then we can calculate the apparent power, the volt amps of the circuit, and that is the total voltage times the total current. 2564 amps, and that equals 30.8 volt amps. And finally, we can calculate the power factor. There are a number of just different ways you can calculate it. Again, look at the chapter or Appendix B. The formula I'm going to use is the voltage across the resistor divided by the total voltage, 30.8 volts. I'm getting that from up here, divided by 120 volts equals 0.257. In percentage, that's 25.7%.